This conference will now be recorded.
Thank you, Lance. Thank you, members of PPI. This is a great opportunity to share with you what I've been learning about modern pipes and fittings and how to increase customer satisfaction. I really want to thank you all, and some of your members in particular, for supporting the work that we've been doing on the research into modern pipe and fittings. In particular, Gary Morgan and Rich Houle have been with me on this exercise and journey for many years, helping us think through methods of test and how to look at the systems and making sure that everything we do seems reasonable and plausible. So I really want to thank them all very much. All right, with that, let's get moving. I have several topics today. What are we aiming for? Where did all the pressure go? Hot water flow in buildings, time to tap and volume until hot. How do we increase customer satisfaction? And then how does all this affect water and energy modeling for premise plumbing systems? And then finally, a discussion. I'm hoping we'll get time for a good discussion back and forth for how we might proceed into the future. All right, what are we aiming for? People want water flowing from their showers to feel right, their toilets to flush first time, every time, clean clothes, dishes, and bodies. In short, the service of hot water, and that as efficiently as possible. They want the services of cold water too. And it doesn't make sense to discuss efficiency until the desired service has been provided. Anybody remember the toilets that came out in the mid-90s after the federal government changed the rules? First, it took more than once to flush your toilets properly. First time, second time, third time's the charm. It doesn't matter how much water the toilet used. It's not a good toilet. It has to work right first. Anybody remember showers that sort of felt like a mist, not like a shower? I like a shower to feel like something. I need to know that it's there. Some people like the misty showers, but not me. And so we have to discuss the service before we can discuss its efficiency. This is a typical simple hot water system. I spend most of my time working on hot water systems as opposed to cold water systems, although that's changing over the last several months. If you look carefully on this diagram, fuel comes into a water heater, whether it's electric or gas or oil, and energy, usually electricity, goes to some hot water fixed appliances, typically washing machines, dishwashers, that kind of thing. Cold water comes in and goes to the water heater. Hot water usually comes out of the water heater and goes to those same fixtures and appliances, and mixed temperature water runs down the drain, going back to the sewer. This simple system is in an enormous number of buildings, whether they be homes or offices or big buildings like box stores. This is a typical simple hot water system. I'm going to use a lot of examples about housing because we live in it, but the principles apply to all buildings. It's just the scale. Now, when we get to bigger buildings, we tend to get more complex stuff. And you tend to, as the buildings get bigger, we tend to put mechanical rooms, and we put boilers or big water heaters in the mechanical room, and then we have circulation loops to bring the hot water closer to the apartments and fixtures. Well, close is a term that is usually given in distance, but I give it in volume. And I'll discuss that more as we go. For hot water, there are two key services. I've been interviewing people about hot water as a system for over 25 years now. And what people have told me is they want hot water now, and they never want to run out in their shower. And they'd like a third thing. They'd like a parental control switch for their teenager showers. And that they appear to be willing to pay more for the control switch than they are for the water heater itself. And so to have hot water now, you must have a source of hot water available before the draw starts, and it must be close to where you need it. Never running out is a combination of burners and storage tanks, and you just have to match the sizes properly. In general, it appears that it's a third shower in a row problem. So the next piece, where did all the pressure go? Well, let's look at a second floor shower. Let's imagine you start with street pressure out here at as high as 80 PSI. Most of us don't get 80 PSI. I've been measuring mine recently, and it's typically 75 PSI or less. Going up vertically, you lose, 0.43 PSI per foot, so about 9 PSI a drop. The tub shower valve loses a bunch, and I picked 11 to make the math work right, but this is right in the middle of the range of the product that we're talking about, because we haven't told you the flow rates yet. And then I decided the losses in the plumbing and the fittings is 20. And I picked these numbers to get the following example to work out of a pressure drop of the losses equal to 40 PSI inside the building from the entrance to the shower head itself. And that gives me a range of 20 to 40 PSI of actual operating pressure. I'm not picking on the piping or the fittings. I'm just using it as an example to show the problem that if you start at 80 PSI, you are not going to have 80 PSI to operate your showers. That's one of the problems of the design. And as the manufacturers of the plumbing systems, sometimes you all get yelled at for other problems in the building, and that's just not fair. The key is this: at 40 PSI, you only get 0.7 of the rated flow rate at 80 PSI, and at 20, you only get 0.5. Okay, and it's actually half the square root of 2, but these are good approximations. And we could do the same thing with faucets. This is just an example of a shower. It doesn't matter what you have at the city. If you have less in the building and your faucets or showers are rated at 60 to 80 PSI, you're going to have less than rated conditions for the operation of your appliances and your faucets and showers. So it's not gonna feel right unless you pick the right faucet aerators and shower flow regulators. Okay, number 3, water flow in buildings. What percent of time does water flow through the meter into the building? Lance, you want to hazard a guess?
Yeah, I'll guess 12%.
Yeah, maybe. That sounds high. Right? So in most buildings, the normal condition is off. And in a fair number of housing we've measured, single family housing, it's off 96% of the time or more. Right? It means it's running less than an hour a day. Sometimes it's 2 hours a day. It's really not very much. Okay. And in multifamily, we've been measuring a bunch of buildings in upstate New York recently, and the water flow, hot or cold, is typically off over half the time, even in a multifamily building where you've got lots of occupants. These are units, apartments with 30, 40 people, 30, 40 apartments in them. So the most normal condition, the second most normal condition, is one fixture, fitting, or appliance. It's probably a faucet. And the real question then is what percentage is hot and cold, because the hot water is leaving the mechanical room, because there is a mechanical room, right? Or the place where your water heater lives. And in homes, of the remaining 4%, the most normal condition happens more than 3.9% of the time, and hot water is roughly half of whatever you think those numbers are. And in many of the homes we've measured, flow rates greater than 3 GPM occur less than 0.1% of the time. Well, Hunter, who developed the methods of pipe sizing, was looking at a 99th percentile peak flow, and this is the 99.9 percentile peak flow. The 99th percentile peak flow is less than 3 gallons a minute. So why are we sizing for 12 and 15? I don't get it. So it turns out that pipe sizing rules were written down in the 40s. Pressure and temperature balanced shower valves became widely available in the 80s, and pressure compensating orifices became widely available after 2010. These are useful because these two devices mitigate many of the issues that many of us grew up with. Does anybody remember doing the shower dance? 2-handled shower valves, and someone flushes a toilet, you have to get out of the way fast because there was nothing to protect you from rapid pressure change. We need to take advantage of these two devices as we move forward into plumbing design, okay? Because they help mitigate many of the problems that had to be designed for way back when. We don't have them anymore. We don't have to have those problems live in our buildings anymore. All right, let's go on to time to tap and volume until hot. All right, more water than is in a pipe comes out of it before hot water arrives. How much more? Lance?
Good question. More water than is in a pipe comes out of it before hot water arrives. So are we saying that if there's 3 gallons worth of water in the pipe, that we normally turn the water off before the hot water actually gets there?
Well, that happens too.
Okay.
So let's work through a couple of examples. Imagine there's a gallon of water in the pipe between the water heater and the fixture. Okay. At a minimum, we have to heat the pipe, right? So something extra is going to come out. And the question is, how much more before the hot water actually reaches the fixture? And so Carl Hiller measured this in the early 2000s for 3/8 to 3/4 inch pipe, and Jan de Zhang measured it again and reviewed the data a couple of years ago, and basically found that for flow rates of 0.5 to 2 GPM in 3/4 inch pipe, 1.5 to 2.5 times the volume comes out before hot water, 105 or hotter, arrives. Roughly 2 to 1. So if you have a gallon in the pipe, you'd expect roughly 2 gallons to come out before hot water reached the other end of that pipe. And a gallon is, in 3/4 inch pipe, well, heck, this is the industry that makes this stuff, is on the order of 50 feet in plastic pipe. It's about 3/4 inch pipe, it's 50 feet for a gallon. And 50 feet of plumbing inside a building is not very far. So it really is very typical to see at least a gallon between the source and the use. And so we're expecting to see roughly 2 gallons come out before hot water gets there. This fact has been known since the early 2000s. It's almost 20 years, and it has not yet made it into engineering calculations. That's a mistake. We need to add this factor in. Can't just ignore it. It has real terms for performance and customer satisfaction. And so if you want hot water to arrive within 10 seconds, which is ASPE's acceptable guidelines, then you have to make sure there's no more than 5 seconds of volume in the pipe between the source of hot water and the use. And I know I'm confusing time and volume and distance all in one thing, but they're interchangeable to me. And so we can talk about volume in terms of time because time's related to volume by flow rate, and you just have to work backwards. But the key here is that we need to decide on how long we want people to wait and work backwards to design our plumbing systems, not work forward from the street and figure out what we're going to end up with. These are decisions that in my opinion, should be made long in advance before we do plumbing design. And so here's a page showing you the calculations of time to tap and volume until hot. And then this is the straightforward calculation. So you get the numbers and all that math is clear. This is how you get the actual numbers. And then you have to double it to get actual time to tap or divide by 2 to get the result you want here in time to tap. Either way, you have to approximately 2 times. Okay, now, how do we increase customer satisfaction? This is the key piece that's been my concern for many, many years. And what I'm after doing is to figure out the simplest ways and the best ways to get better performance for customers in their buildings. And my focus for many years and still is on the hot water system. As we learn more about what people care about in cold, we'll focus on that too. All right. The titles of these sections sort of follow the outline you just saw. So reduce the distance from the source to the use. The shorter the pipe, the less time it takes. The smaller the pipe diameter, the less time it takes too. But somebody external is lowering the flow rates on us, so it takes longer. We need to decide on how long. 5 seconds, 10 seconds, longer, shorter, I don't know, we have to pick. In my interviews over the last 25 years where I've done classes and webinars and seminars just like this one, I've asked this question of how long people think they want to wait. And in general, way more than than average, like 99% of the time. People say we want hot water within 5 seconds. Well, that means you can't have more than 2.5 seconds between the source and the use. Well, how does that work out in pipe length and pipe volumes, right? You've got to figure out how to build a building. The key, in my opinion, is that the decision on the location of the wet rooms and the mechanical rooms is made by the architect. And we need better floor plans to get better plumbing. We can't make it the responsibility of the plumber to figure it all out. And so we have to work with the architects to give us better choices. This is an example of how we might look at the distance between the wet rooms and the water heater. And this is a house from Fresno, California that was being sold last year, maybe the year before, probably still is. Notice the water heater is out here in the garage. The rectangle tells me it's tankless. It's on an outside wall. And then you've got the second bathroom is over here on the right, and the kitchen is over here, and the master bathroom is here, and the laundry room's in the middle. So we could create a rectangle having to do with just the wet rooms, and then we could have a separate rectangle for the hot water, the water heater plus the wet rooms. And we might be able to make them a little bit more refined, but the idea is to create a bounding condition for the area taken up by the hot water distribution system. And you'll notice that here in the kitchen, we didn't bound the whole nook and great room. We bounded the area where the plumbing is likely to go to get into this wall here. And we had to go all the way out to this wall on the side because of the water, the tub here. We could have shortened this up a little bit because the water heater is here, and we could have run this right over here in the middle. But the idea is that it's approximately 67% of the floor area of the dwelling. It's a technique we developed in order to analyze floor plans efficiently and effectively. And it's useful because plumbing tends to run in rectilinear fashion. It gets hidden in the interstitial spaces, which tend to run that way, and that's where the plumbing goes. So we follow the rectangles, not diagonals and circles. So there is a relationship between the hot water system and the floor area. The logical worst case is that in a one-story dwelling or building, the water heater is in one corner and the furthest fixture is in the diagonally opposite corner. That's the logical worst case. If you have 2 stories, then it would be, for the same floor area, you'd have half the distance because it's floor over floor, 3 stories, etc. Here's the kicker. You can do worse than the logical worst case. So far, the most spread out floor plan we've found is that for a floor area of this, the hot water system was 50% bigger. Why? They had one hot water system for a house with a huge courtyard and a guest suite that was off the main courtyard. No wonder distances grow very, very quickly. And they only wanted to put in one hot water system. I'm not quite clear why. This was an over 5,000 square foot house. I'm sure that the budget could afford 2 water heater systems, one for the guest suite, one for the rest of the house. The hot water system costs way less than the tile in the bathroom, let alone what goes on in the kitchen. So this chart comes from the ASPE time to tap performance criteria, as shown at the bottom of the slide. And acceptable performance is 1 to 10 second, marginal performance is 11 to 30, and unacceptable is 31 or more. Well, let's not aim for the red, although often we get it. And we have to decide what flow rate we're designing for. Now, if I asked you all how long your plumbing is likely to last, each of the material products that you all sell, I'm sure you're going to tell me it's on the order, should last at least 50 years in domestic hot water and cold water applications, right? It's way more than 10 or 15. So let's design for sort of like 50. Over the next 50 years, do you think somebody might come around and decide to change the flow rates from what they are now to something else? And what do you think the odds are that it might go lower? I think the odds are pretty high. So I'm currently doing my design work and thinking for all fixtures other than public lavatory faucets. I'm using 1 gallon per minute on the hot side. And for public lavatory faucets, I'm actually using 1/4 of a gallon per minute. And the reason for that is that half-gallon per minute public faucet aerators, which is the law in the United States, are actually many hands-free. And if they're hands-free, it's sort of like you have half hot, half cold. And so if you actually want hot water to show up for a hand washing event at a public lavatory faucet, whether it's in a public lavatory in a home, doesn't matter. You have to design for these lower flow rates, maybe as high as this if they're not hands-free, but this is how I do my design work. So at 1 gallon a minute, if I want hot water to show up in less than 10 seconds, it would be in here. It can't be more than 10 ounces in the pipe to get there in 10 seconds. Okay? That's not very much, right? How, you know, if you're 5 to 7 feet tall, 5 to 6.5 feet tall in the United States, you're equal to 8 ounces of water in half-inch plastic pipe. Okay, so it's a little bit more than our height. Well, that means the source of hot water's got to get very close. I live in a part of the country where we don't do basements. We plumb from above down to the first floor. That's what we would do inside a basement in homes that have them. We plumb from the ceiling of the basement down. It takes almost 8 feet just to get down to the angle stop for a sink valve. There's not a lot of room to play with here. It's tough to get within 10 seconds, but we have to make a decision of how we want to design and build the buildings. And the reason I use 1 gallon a minute for everything except public lavatory faucets is that if you actually have 2 gallons a minute now and someone brings it down to 1 later, if you decide for 1 now, everything's going to show up quicker. No one will complain. I'm into the no complaints over time rule. All right, now let's talk about right-sizing the plumbing. I'm not sure that any of you on the phone actually do pipe sizing, but this is a question I ask lots of people all over the country, and there's lots of different ways to do pipe sizing. And I'm just sort of curious as to what people use, right? Well, it turns out that the ways of estimating peak flow rates, there's 2 methods that are widely used. One is the water supply fixture unit method. It's used in the IPC, the IRC, and the UPC. And it's the method we've used since Hunter developed it back in the 20s and 30s and published in the 40s. Great. In 2018, the Uniform Plumbing Code developed and adopted an Appendix M as in Mary with a water demand calculator that brings the Hunter's method into the modern era with real flow rates and realistic probabilities of use for residential applications. It's not yet available for use for all building types, but it's available for all residential applications. So I think it's very applicable to apartment buildings of any number, single family dwellings of any number, whether they're stacked in apartments with their own water heater or not, doesn't matter. Central water heating systems for multifamily. I actually think it's probably pretty applicable to the bedroom wings in hotels and motels. They act residential, not commercial. Okay, but there's another question here. What if we could use real data for different occupancies to size with? Because if real data is, I don't care what the estimates are. The question is the estimate going to give you a good plumbing system? And if you have real data, why couldn't we really use it? It'd be very interesting. So here's a pipe sizing comparison for a 35-unit apartment building in upstate New York that we've been working with for some months. And using the 2018 IRC or IPC, which is what they use there, the methodology says you're going to see a peak flow of about 7.5 to 8 gallons a minute, hot or cold, cold or hot, and you need 3/4 inch pipe to service that. And it's based on PEX analysis. I looked at copper and I looked at PEX, and they're building with PEX, so that's what I use for the method. And if you take, and then you have for 35 units, you're expecting 51 hot, 50 cold, and 70 gallons per minute coming into the building, and you need a 3-inch pipe. Okay, we did the analysis using version 1.4 of the water demand calculator, and we came up with 3.6, 3.6, 12, 13, and 16, and you can see our pipe sizes. So we get a 1 pipe size change on the entrance into the apartment, and we have, 1, 2, 3 pipe size down here, 4 here, 3 here, 3 here, and 4 pipe sizes here. That's a big difference. By the way, it transfers through to all the other equipment in the mechanical room, like the PRVs. Probably ought to transfer to the meter. It ought to transfer to the service entrance, right? And so you need to know this information really early on in order to affect the cost of construction, as well as affecting the future of the operations of the building. And now we've been measuring this. My colleague Pete Skinner in upstate New York, who got me involved with these projects some months ago, has been measuring with with a series. We have a what he calls a magic box, which has several external flow meters, ultrasonic flow meters we can strap onto the plumbing, and a bunch of temperature sensors, so we can figure out what's going in and out of the mechanical room. The measured 99th percentile peaks in this apartment building, one of the buildings right next door to where we're building the new stuff, 35 unit apartment building, it's less than 3 gallons per minute hot and 5 gallons per minute cold. Those are the 99th percentile peaks. The code is suggesting that the 99th percentile peak is 51 and 50. The water demand calculator version 1.4 suggests it's 12 and 14 gallons a minute. And we're only measuring 3 to 5. I don't think we need a factor of 10 or more safety here, because I'm not certain that that's safe anymore. Right? Things grow in our plumbing systems, and they grow nicer and better when, from their perspective, if the flow rates and the velocities are slower. So daily hot water use turns out to be about 15 to 20 gallons per apartment per day in this occupancy. All right, pipe sizing using the water demand calculator. We went into the nomograph that your industry provided to the Uniform Plumbing Code. And the Appendix I, 2018, is what we used. I would note, by the way, that there's a minor error in the chart. You should check out the official publication, but that's the wrong number in the chart. So I put the right number in the chart. At least I think that's the right number. And you can see that we're sizing for peak velocities, peak flows at peak velocities in this range of 5 to 8 feet per second. And I'm going through and doing the pipe segment design so that I'm maintaining velocities throughout the system at peak in this range. That's my target range. Why? Peak is the 99th percentile. What are my normal flows? My normal flows are not up here for the one apartment, right? They're down here at 2 gallons a minute. And at 2 gallons a minute, if I still would like my velocities to be in here, but they're going to be here if I pick 1/2-inch pipe, right? I'm going to be here. So my velocity is like 4 feet per second at realistic flow rates. Well, that's fine, but I'm trying to keep the velocities reasonably high most of the time. That's the plan.
Gary, sorry to interrupt.
Sir.
Can you clarify again the horizontal pink line in the left graph? Where?
This one.
Yeah, what is that based on?
That's based on what we developed for the peak flow rate from the water demand calculator. So that's 2 gallons per minute, right here, and that's 4, and we came in at 3.9.
Yeah, okay.
And so I'm using this line, and hot and cold were the same, so that's why they're overlaid. And we're designing for here at 1/2-inch pipe. But, we certainly don't want to see 3/4-inch pipe. While that would be typical, it's way too low a velocity for peak. Remember, this is a peak sizing question, right? So we'd want to be out here in this 5 to 8 foot per second range, with the expectation that 99% of the time or more, it's going to be over here somewhere. That's the peak. It's not going to be at 3.9. It's going to be coming down, in flow rate. Let's imagine it's 2 gallons a minute. All right. Well, a 1/2 inch pipe would be here. So I'd have less pressure drop per foot for sure, but my velocity is less than 4 feet per second. Still respectable and still good, but I don't need to design it for that purpose. I need to design for peaks in the 99th percentile out in here. And then we did the same thing for the whole building, and the color coding is a little different here, not too much, but the idea is the same idea. I'm designing for 5 to 8 feet per second, and I want to pick my pipe sizes in here somewhere in this range for peak. And that tells me 1 inch, 1 1/4 inch for the cold water entrance, cold water main, and that's what we're building now. Now, it turns out that the water demand calculator, so we're building 3 buildings with this pipe sizing set of rules implemented in them, plus some a change in the hot water system layout that we came up with that saves several hundred feet of pipe in the building and allows us to direct the water better where we want it to go. And so we'll get results sometime later this year. They'll start occupying the buildings, and as soon as we get results, we'll start to talk about them, good, bad, or otherwise. Right? We did a design. We hope to God it works right. But all of the data that Pete's been measuring suggests that the flow rates are, they're not up in here for the whole building. We're measuring flow rates that are down in here for the whole building. 4 to 5. That's where 4 to 5 is. And so we think this is a pretty significant safety factor already, and we should be fine with our pipe sizes. It turns out that IAPMO has developed a version 2 of the water demand calculator with updates on how to handle multifamily apartment buildings. And if we run the same building using the water demand calculator version 2, we come up with peak flow rates down in here, and it means that the entire plumbing system can be 1 inch pipe or smaller. We don't need 1 1/4 inch. That's rather amazing. We went from a 3 inch design by code to a 1 inch for the whole system based on updating what Hunter did 100 years ago practically, and bringing it into the modern era. It's a very, very powerful tool, and I cannot recommend enough that you all start to play with it. Particularly those firms that give out advice as to how to design plumbing systems. I would be at a minimum cross-checking all the code math with what we can do in the water demand calculator math, whether it's used for uniform plumbing code or international plumbing code or any other code. The math is very, very telling. So the next item is reduce the pressure drop in modern pipe and fittings, because we need to do that. So what is the pressure drop in modern pipe and fittings? We have many materials, calculations versus measured data. Are what we're using, are the data we use representative of present day materials and fittings? And so it turns out ASHRAE has a pipe sizing committee, and they've done some work on trying to trace the history of what's been done. And it's very telling, going backwards in time. Hedberg and Rahmeyer did some work in the 90s and they discussed the origins of the data and tables. The Hydraulic Institute, 1990 data, which goes back, if you trace it backwards to 1960 or 70, their data appear to have come from Freeman's work in 1941. That's actually work done by Freeman's dad, performed in 1892. And it turns out I know the great-great-grandson. And I was at a conference a decade ago, and this guy shows up and says, "Hi, I want to show you a book from my great-great-granddad." Okay. And we looked at the research, and it's absolutely impeccably done research in 1892, but it's for steel pipe and threaded and flange fittings. I'm talking with an industry that didn't exist for making plumbing materials back in 1892. And it was updated in the 20s and 30s by Gasecki and colleagues, and for copper. And I'm pretty sure, because I can't find the paper, but I think they updated it for threaded and flange copper fittings back in 1892, back in the 1930s. I don't know when soldering became widely available, but my instincts tell me that the research was done for threaded and flanged fittings and copper pipe, straight copper pipe. Okay, well, what about what we use now? So several years ago, I've been on this quest for many, many years now. And I talked with, people in this room like Gary Morgan way back then, and Rich Wool more recently, and Lance as well. And I asked, well, how do you measure pressure drop in pipe and fittings? What's the method of test? Is anybody doing it? Can I get data? And the answer was, huh? Well, that's disturbing. If we're trying to right-size plumbing, we better have some good data to move forward, because everybody in the plumbing industry I know is from Missouri. We're going to have to show them. So let's find some data. So we set up a lab to do it. We have a lab down in Southern California at the Southern California Gas Company's facility in Downey. We don't have a permanent place to do our research, so everything is on a movable cart. This cart is designed for two things in mind: to give wide radius elbows when I need to make wide radius bends in the pipe, and it has to be skinny enough and short enough to get through the door so I can get in and out and go to my storage location. And so the lab has available to us to use hot and cold water source pipes. We built up a rack that includes a flow meter, pressure and temperature sensors at the beginning of the experimental section, and pressure and temperature sensors at the end of the experimental test section. And we set up the ability to measure pressure drop through a variety of pipes and fittings. This rack has on it 3/4 inch down to 1/4 inch tubing. That's what we've been able to put on there. And we've modified this rack several times. And I think there's close to 1,500 feet of pipe on the rack. And I will admit, it's not the prettiest plumbing job in the world. It's practical. I'm trying to learn what happens in the piping. I'm not trying to make it look absolutely perfect. Want to learn what goes on in the fixtures, and in particular the fittings. The concept here was to create a series of pipes with and without elbows of the same length and the same number of fittings, so that we could observe the pressure drop through the pipe and the fittings, and subtract the pressure drop of the pipe with the fittings from the pressure drop, subtract the pipe without the fittings from the pipe that has the fittings, and you get the pressure drop for the fittings, divide by the number of fittings, and you get pressure drop per fitting. We did this multiple fittings idea because we knew the limits of our experimental setup. We felt it would be very, very difficult for us to accurately measure the pressure drop through one elbow or one corner of a T. And so we set up several, and we just averaged over the whole system. You can see here that we have a real-time screen that watches the data points, and we can literally watch experiments in real time to make sure we're doing a good job of our experiment before we spend half an hour doing a test and find out we have to do it again. Turns out to be valuable. We learned a lot from that lab. And since then, we set up another lab up in Arcata, California, with some colleagues there who are associated with hiring interns, mostly from Humboldt State University. And so we've modified the system to have fewer feet of pipe and a consistent number of elbows. This rig is showing you a rectangular spiral of CPVC with 10 elbows in it. You can see that's actually Pete Skinner, who I mentioned earlier from upstate New York. He and I are preparing sections of expanded PEX so that we can make up another segment so we can keep testing. We have some, you can see our test card in the front here, flow meter, flow control valves, water inlet is over here, comes up through this P1, T1, goes out to the test setting and back through P2, T2, through the flow meter and discharge into the bucket. The bucket goes out into a field, and the field is where they grow crops. So we're not wasting water. Seemed to work pretty well. We've measured elbows widely spaced and close together, velocities from 1 to 12 feet per second. And so far, we have not yet measured anybody's published numbers. This is disturbing. I should have tripped over a few of them by now. Are our measurements higher or lower? Yep, they are. Both. Do our numbers have the same trends as what is published? No, this is even more disturbing. And all this matters if we want to right size our piping systems. We've got to get numbers that we all believe to be accurate and true. So more on pressure drop. Is there a minimum radius of curvature through which there's no additional pressure drop other than that due to the length of the bend? The answer is yes. Wouldn't that be the most water, energy, and pressure time efficient bend? Yes. Ask me about the swoop later on. We'll get to that. We've measured pipes. It says 1/4 to 3/4 inch. That's what's in this description, but we've gone down to 1/8 inch and we've done some work at 1 inch. I'm focused on the small end of the plumbing system because we're trying to right size for lower flow rates. Why would I be worried about fatter pipe? We have to do it. We need the data, but I'm focused on the smaller pipes. More examples. Copper. We've looked at a bunch of different elbows in copper. We've also looked at T's in copper, but this is showing the elbows. And here we have tight inside elbows. In fact, these are not the tightest that we can find. The tightest elbow would literally be a hard 90 corner. And if you go to the big box stores, you get hard 90 corners. And if you go to the plumbing supply houses, you actually have a nice tight inside radius corner, which makes a big difference in the pressure drop. Long radius sweeps, swoops. Here's some PEX elbows, lots of different PEX elbows. Manufacturers have different ones. We use this generic naming convention, but Lance and I were talking about it the other day. Perhaps we ought to update these names to the standards for which they apply. I think we may need to do both. If you want to talk to people who are outside our industry, they don't know the standard from a hole in the wall, but they can tell that that's, you know, a brass fitting or something like that. Bend supports, different elbows, different dimensions, couplings, T's, again, different styles. So what are the results? This is looking at copper, 1/2 inch copper. And so I need to go through this before we go into a little bit to give you an overview before we go into detail. Down here, whoops, sorry. All right, here at in the bottom is the target flow rates for 1/2 inch pipe for PEX, CPVC, and copper. And the reason we need a target flow rate for a given velocity is that I have to set up the flow rates with the valves that you saw to give me my flow rate. We're not spending several $1,000s on one valve to give us a very accurate flow rates down to the 100th. We can get our flow meters is accurate down to 2.9 gallons a minute. And we can hold it there. If we have steady pressure, we can hold that flow. And so 2.9 is close enough to 2.91 for us to get a reasonable curve. And I'm into the practicality of it all, not the perfection of it all. I want to be close, right? Real close. And so we can do that. So we have our target velocity at 2.9. Why did I pick 4 for this conversation? Because 2.9 gallons per minute is higher than the 99th percentile peak, even in apartment buildings. Okay, so why can't I be thinking about that? Why am I worried about 6, 7, 8 gallons a minute? I don't care. I'm not going to use 1/2 inch pipe for that. So what I want to do is to work out what's the pressure drop at realistic velocities, and that's 4 feet per second here for copper. The other thing is that it's actually, many of our devices are less. They're at 2 feet per second. Well, the pressure drops at 2 feet per second are really tiny, so they're less of an issue. I'm worried about what's happening at these velocities. I don't really care out here for these. They shouldn't happen very often, if at all. And so at copper, you can see it ranges from just under 0.05 to just over 0.05. And for this discussion today, we're going to say it's about 0.05 PSI per fitting with some variation. Okay, we have not yet tested couplings or run through T's, right? Run to run. It's sort of silly. We can do it, but you know, all we're going to really learn about, in my opinion, is how well we ream the pipe. And I haven't quite yet figured out how to make a standard badly reamed pipe to test what happens if I do a bad job. When I do, I promise to run the test. I think we have to do it. On this scale is the copper shown against what we found from our PEX measurements. So you can see that copper has relatively small pressure drop per fitting in, fine detail and in the bulk sizes based on what we measure for other materials. Moving on. Here's the pressure drop in 1/2 inch CPVC. Well, there aren't as many fittings to measure in CPVC as there are in some other things. So this is, a typical set of pressure drops for fittings that we would find. We did CPVC branch to run and run to branch. We have not yet done run to run through a T, and we haven't done couplings. Again, they're external, so that they should have very little pressure drop. We will ultimately get to measure them. We just haven't done it yet. And we also picked 4 feet per second because 2.3 is still pretty close to the peak that we'd expect on a fixture branch, or what I would call a twig. Lance, do you have a question? I see your green light is up.
I do, thank you. Yeah, can you explain the difference between the graphs on the left and the right?
Sure, I will do that. The graph on the right is scaled it's scaled here. The y-axis is scaled so you can see how CPVC or copper compared to what we found in our measurements of PEX. So all of our PEX measurements, some of them had pressure drops up here in the 6 to 7 PSI range out at 10 feet per second. And so I'm showing these numbers on the left scaled to the numbers we found for all the fittings we've measured so far. Same data. Both numbers are the same on both sides. It's just how it looks 0 to 1 versus 0 to 7. Does that explain it, Lance?
Yeah, perfect. Thank you.
All right, good. All right, so moving on. Again, I'm using 4 feet per second because 2.3 is still higher than most of the flow rates we would see for most devices a 1/2 inch pipe would be attached to. I'd consider going up to 6 feet per second, but maybe 5 feet per second, but we can interpolate for all of that. So at 4 feet per second, the pressure drop is a little over 0.1, 0.13. It's roughly double that of the copper. Okay? Not exactly, but roughly. And that's a useful thing to keep in mind. So the next slide, this is the PEX. All right. So for the PEX, we did couplings and T's here on the left, right here, and elbows here on the right. You're going to get this and you'll be able to study it and ask lots of questions at another point if you wish. I'm happy to give you and your companies specific conversations about this. I think it's useful to go into details. I'm looking for advice on how to have done it better, and if we move forward, how to do it better going forward. But here's what we have. Again, at 4 feet per second, because most flow rates we'll attach 1/2 inch pipe to are really less than 2 gallons a minute, right? Showers, legal maximum flow rate for a shower in the United States is 2.5 gallons per minute at 80 PSI. And unless you've got 80 PSI, you're not likely to have 2.5 gallons per minute, and it's not likely to be all hot or all cold. It's likely to be less than 2 gallons per minute on each side of the plumbing system. And so we're going to use this number, 4 feet per second, as our current estimator. And you can see it ranges from not much above 0 to about 1 PSI per fitting for a variety of fittings. And the same here for the elbows. It ranges from 0 up to about 1. And the key at 0 is it's a bend support. And a bend support's an awful lot like a swoop. And getting people to use more bend supports than hard 90 elbows is a really, really good move to reduce pressure drop in the plumbing system. Look, you have to have T's to get water out of a trunk into a branch. You have no choice but to do that. And if you're using straight pipe, you're going to have to put couplings because you don't have always the right distance between T to T, right? Or the T, the branch of the T to the fixture in question. But that tells me we should be using coiled pipes to cut down the number of fittings, and we should be minimizing the number of fittings to T's, beginnings and ends. That's it. Try and minimize the number. Why? Less pressure drop. Why? Gives better performance at the end device, which is what we're aiming for. Look, I understand the implications for costs and sales, right? I get that. A lot of what I'm talking about right sizing is going to make pipes smaller than they are now. And okay, there may be less profit in the smaller pipe than in the bigger pipe, but we want to do the right thing. And so we have to talk about how to do it correctly. I see a question, Lance. Do we need to address it?
The question was, what connection style was used in the PEX evaluation? So it looks like on your graph, you've got 8 different lines, 8 different colors. The descriptions in there are a little tricky to read depending on the size of your monitor. But for instance,
well, this is it. We have expansion tees.
Yeah.
We have expansion fittings. We have press. We have, these are all showing. So we have press brass and press plastic. This is named badly. Polypress brass doesn't make any sense. That's brass, that's plastic. I'll correct those before we send out a final, okay? We did crimps. We did push to connects. We didn't do push to connects on everything. We did push to connects on the elbows. So we've done, oh, let me back up. It's faster to go backwards.
Well, I think where it says, yeah,
we did all of these.
Yeah, so
all of these types.
Polycrimp, that would be what we would call ASTM F2159. Brass crimp would be F1807. Poly expansion would be F1960. And brass press would be F3347. Polypress.
What are the push to connects outer seal? This one versus this one.
Are
they the same standard?
ASSE 1061.
Thought you might know, Rich.
Imagine that.
So,
hey Gary,
yeah.
I do have a question when you get back to your table on PEX. But
so before we get there, yeah, almost there. So, and here's what you can see in some of the couplings. I have to thank your industry for helping out by providing materials. And so I asked Rich and Gary and others for providing materials to this testing. I'm currently funding the testing out of my own money because there are no clients that are obvious for this yet. I'd love to find a client so we could do it all and do it all correctly and have a standard method of test that everyone would agree to use. And we just run all new materials through it. So there's an independently published set of things. But we've been running this on a bit of a shoestring, and I've had great support from your members to help get me the materials we need for the testing. And so we get what we get, and right now we can't go to test very much because of COVID, right? So we're not going to get much done for a while. As soon as we get back up and running, I'll start more tests. We could talk about that. All right, so back to the PEX. Here we go. Rich, you had a question.
Yeah, I'm scratching my head a little bit looking at the data, and then the very last statement that's at the bottom, it says at 4 feet per second, the pressure drop ranges from 0 to 2.5 psi per fitting. But
Whoops.
When I looked at the graph, it looks like it should be like 0 to 1.
You are correct. I made a mistake. Good catch. I was debating in my mind when I did this, am I at 4 feet per second or at 6 feet per second? And if the 0 to 2.5 is at 6, and at 0 to 4, at 4 feet per second, it should be a 1. And so I apologize. Good catch, Rich. I will fix that too. Which should I put? Should I put the footnote at 6 feet per second or at 4 feet per second?
Well, considering you're using 4 feet per second in the example, I would suggest 4 feet per second. But
all right, it doesn't matter. The point is the same, that the pressure drop varies and it's by velocity, and I'm still having trouble figuring out the velocity, the pressure drops that have been published, because there's no footnote that tells me the velocity. Based on conversations I have, I think that most of the published pressure drops through fittings and pipe are at 8 feet per second. That's nice. Why not 10? Why not 6? But they don't say that. So I'm assuming that the pressure drop is the same as I go down the curve. It's just not true. Right? It's roughly half every time you go 2 feet per second different. So that's a big difference. Anyway, I will adjust this to make it all match for 4. Great question. So we tried to figure out, can water make a 90-degree turn without losing pressure? And you saw the benefit of the bend supports. This is showing how the bend supports compare to a variety of ways of measuring sort of straight pipe. Well, the blue line here is straight pipe. The red one is a large radius curve going in and out of our test rig. Green is a coil of pipe. I don't know, the manufacturers ship out coils in the sort of 2 to 3 foot diameter range. We pretty much use one of those coils and connected it up. And then the purple line is bend supports. And you're going to see differences as you get out here to 10 feet per second, 6, 8, but down here at 4 to 6 feet per second, which is the range we're interested in for the most part, these differences are within our experimental error. And so I would say that they're sort of the same. And I'd say these are sort of the same. I'd say even these are sort of the same too. But we're in this range. What are we talking about? The difference is less than 0.01 between all 4 of these. They're the same for practical purposes. Lance, I see a question again.
I don't see anything new.
Okay, not to worry. I just saw green, that's all. No big deal. So the key here is that bend supports help the water act as though it's in straight pipe, yet it changed direction 90 degrees. That's a huge win because it really does allow you to have neat, tight, and straight pipe and still change direction the way you need to do it. All right, the next one. Let's go to 3/8 copper tubing. And this shows you the range for the fittings we measured. We've done this at different times, and so I've date stamped the times, and they're sort of similar, so that's good. We have different temperatures in January than we do in May, and I'm not controlling temperature in our rig. Oh, this reminds me. All of the pressure drops I use in my designs, when I use my numbers, come from pipe with cold water flowing in it because I've measured them with cold water. I have not measured the pressure drops in the latest lab with hot water. We've done some measurements of that at the lab in Downey. But in Downey, the problem we had with cold water is that sometimes it was cold and sometimes it was 80 degrees. And so that's not really cold water. The reason I use pressure drops in cold water for estimating pressure drop in most pipes is that except for recirc loops, the water in the branch pipe is most normally at the building's temperature, which is sort of like the cold water temperatures we're measuring with up in Arcata. And so I know that the pressure drop is less when hot water is flowing through the pipe, but most of the events of hot water use are not at steady state, so they're not actually hot yet. So it's a conservative way of looking at the pressure drops by using cold for both systems. About a 15 or 20%, 10 to 20% safety factor, if you will. So at 6 feet per second, because the flow rates we're interested in might be as high as 2.7 gallons per minute, but again, they tend to be lower. We're going to use 6 feet per second for the 3/8 pipe, maybe even more for the PEX. And at 6 feet per second, the range is here. Sort of 0.15 to 0.3, somewhere in here. And again, this is the right-hand side is scaled to what we measured for the PEX. There is no CPVC that we had available to us at 3/8, so we didn't measure it. And at 8 feet per second, to give this flow rate sort of comparable to this flow rate, okay, we're using 8 feet per second. The pressure drop for bend supports is still 0. They're really a good fitting, up to about 8 feet per second for both couplings and actually T's and elbows, okay? There you go. In rough terms, the pressure drop through pipe at 3/8 versus half is double of its comparable product. And again, looking at 3/8 tubing, can bend supports be helpful? And the answer is yes, they can. Bend supports are essentially the same as straight pipe, and at 8 feet per second, it's about 0.4 PSI per foot. Well, I want to go backwards a little bit here, looking at PEX. If my PSI per fitting, where did it go? Come on, give me my cursor. My PSI per fitting is 8 PSI per fitting in the worst case numbers, right? And I have on the next chart, the PSI per foot is about 0.4. If I take 8 and divide by 0.4, I get about 20. Is that right? So my equivalent length is about 20 for the 3/8 tubing. I haven't shown that here because I want to make sure my method is reasonable. But if I have PSI per fitting and I have PSI per foot of pipe at the same velocity, dividing one by the other should give me equivalent feet. At least that's how I understand it. We've done the same thing for the 1/2 inch. And going back at the 1/2 inch, we're going to pick the same, the 4 foot per second. And this is 0.08. And if we go back one more here to at 4 feet per second, we're down here around 1. 1 divided by 0.08 is about 12 equivalent feet for the fittings. Again, worst case. There's others, there's many that are better, but I'm using the worst case to give a bounding. Worst measured. I'm not sure it's actually the worst case. Here we go. All right, moving on to the next item. I showed you earlier in the pressure drop slides that we have, where did all the pressure go? That there's pressure drop through tub shower valves. Well, what is it? I couldn't find published numbers. I know it's there in some commercial catalogs, but I can't find it. I looked. I spent a lot of time trying to figure that out. And so I decided to go up to the lab and measure them. And we did this late last year, early this year. And you can see there's a bunch of boxes here, and I went to the big box store and got a whole bunch. And I went to the lab and I measured them. And I have the data specific to each brand, but I'm not showing the brand names here. Again, we need to be generic about some of this stuff. And so this red dashed line and this black dashed line are shower only valves. The other lines are tub shower combo valves. And let's pick 2 gallons a minute. Actually 1.75. I'm in California. That's the legal maximum for sale in California. This valve has a pressure drop through the valve, and this is measured with hot and cold water coming in, and we're going through the valve and up the shower spout. We've also measured on the next slide going down through the tub spout. Hold on just a second, please. We have a barking dog in the background. I'll be right back. All right, I'm back. Hopefully it'll get better. We're new to having puppies, and as you know, they're exuberant at times. Lance, anything?
Yeah, well, they don't respect the fact that you're doing a webinar, that's for sure. I was going to give you just as a time check, we are at 38 after the hour, so it's been about 65 minutes since we started.
Cool, we're very close. We're good. I think we're doing well. All right, thank you for the time check. So here, we're at about 7 PSI. That's at the best of the bunch that we measured, and the most pressure drop at that is about, whoops, sorry, it went backwards. Be careful not to click. Right here, you can see it's just under 14 PSI, so roughly double from the worst to the best, right? 2 to 1, and that holds throughout the whole range. And so the example I gave you earlier was, I didn't tell you what the exact flow rate was, I said I picked a pressure drop of about 11 PSI for the shower valve, and we're somewhere in the middle of here, right? That's 11. And I'd say that that's pretty good over a wide range of possible conditions. When we get to specifics, we have to know which one it is, but 11 was not a crazy number to pick for the pressure drop through a tub shower combination valve. We've done the same thing here through the tub valve itself. And the question on tub valves is, what's the actual flow rate coming out of the tub spout? Because it turns out that the flow rate out of the tub spout, because they're pressure dependent orifices, there's no flow regulators on the downspout, nor do I think we should put them. We get whatever the pressure gives us. So if we only have 40 PSI operating in our building, we're going to have a lower absolute flow rate because it's depressing the ability of the device to flow water out. And this is looking at the drop through the valve, and the drop through the valve is less going through the tub spout than it is through the shower itself, because the pipe, the holes for the water to move through are bigger.
Gary, one clarification.
Yes.
When you do 2.5 GPM in that previous graph, that's hot and cold combined, right? That's not just one temperature.
That's correct. This is, we actually set the valves to a mixed flow rate condition, somewhere close to the center. And what we did is we looked for the maximum flow rate out of the valve, and then that's where we left it for the tests. Again, there's no method of test for this stuff. We're just trying to get a good sense of what's flowing, right?
Yep.
And I don't know about you all, but my hot and cold water conditions are such that my set point is a little bit left of center, top dead center is the way our valve is set up to be the mixed temperature I'm interested in. And so might be that way, depends how you're looking at me. Anyway, the point is that it's a little bit of off center, but it's close to that middle. And so that's what we set these with, to get a sense of how big the number is. All right. I've spent a lot of time on this, and there's very few methods of tests. Imagine having an ASTM standard for which there was no method. Be great fun. So fixed orifice devices. I want to have pressure independent faucets and shower heads. Fixed orifice devices have high flow rates at high pressure and low flow rates at low pressure, and pretty much before 2000, everything was a fixed orifice. There were very few orifices that were pressure compensated. The aerators became available starting in 2000. They're ramped up for shower heads. I've been talking with the primary manufacturer of these products that sells to all the OEM throughout the United States and Europe. And pretty much 90% of all shower heads and virtually all, more than half of all faucet aerators being sold in new products are coming out as pressure compensating. And I'll show you some of those in a little bit. Here's the big deal. Remember that 80 PSI for the shower head that we started with a long time ago today. We have 80 PSI is the flow rate at which the maximum flow is determined. We'll assume it's 2 gallons a minute. And if we have a fixed orifice device, we follow the gray line. At 40 PSI, which is a plausible pressure at your shower, we're only going to be about 1.4 gallons per minute. If you're down as low as 20, you're going to be about a gallon a minute. Nobody liked the 2 gallon per minute shower heads because we're old enough to remember ones that flowed at 5 or 6 gallons a minute. Well, you're not going to like one. But what if you had a 2 gallon per minute shower head with a pressure compensating flow regulator in it, an orifice, and you'd either be on the green line or the gold line is what I was trying to go for here. And what the idea is that you want to have the highest flow rate you can get over the widest range of operating conditions. That will give customers the greatest satisfaction. They do not want to be on the gray line. They want to be on the green or preferably the gold line. That's the idea. Now, if your pressures happen to be higher than 80 PSI, that most municipalities and most plumbing codes say you're supposed to put in a pressure regulator to get you down to no higher than 80 PSI. So this is a pretty good place to work out our maximums. What about for faucets? I'll pick a 2 gallon per minute faucet aerator. Legal maximum for laboratories in California is now 1.2, but legal max for kitchen sinks is 1.8, so it's close to 2. We'll use 2. At 2 gallons a minute, it's rated. I don't know why this is true. Faucets are rated for flow at 60 psi, and showers are rated at 80. Why they're not the same beats the heck out of me, but I'm late to the game, so a whole bunch of decisions were made a long time ago. Again, the gray line brings us down at 1/2 and 1/4 of the rated pressure. You'd be down in here at 1.4 and 1 gallon per minute. And again, we'd rather be on the green or the yellow lines. That's what customers would want to be have greater satisfaction. And that's what we want to provide. So here's a bunch of different stream types. Most of us don't know, and most of the plumbing industry doesn't know, that you don't have to have all your faucets look like this or this. You get to pick. Here's what some of the insides look like. They're color coded so you can figure out what's going on. At least it's supposed to help us. You can see if you look inside these devices, there's a little rubber O-ring, and that O-ring squishes from this manufacturer. The O-ring squishes under high pressure and relaxes under low pressure and gives you constant flow along those lines that you saw earlier. Here's going down to 0.35 gallons per minute. Below 1.2 gallons per 1.2 and below, they only make pressure compensating orifices because the flow rates are so low that you want to make sure that there's enough room to keep the flow rate high, and you need pressure compensating to do it. This is a dual core O-ring system, and this is along the lines of those orange lines I showed you before. This is a higher performance product than this one is. From an OEM point of view and a customer point of view, the marginal price difference between the fixed orifice and the pressure compensating orifice is way less than 1/4 to the manufacturer, which means it's way less than $1, if any, to the consumer. When you're buying new faucets and showers, this is for faucets, it's built into the price of the product. All right, getting close to the finish line here. So how does all this information affect modeling? Most of us who've been doing modeling of hot water systems grew up thinking about hot water as a series of what sort of looks like sine waves. There's a weekday sine wave where you're coming in the morning, you don't, not too much use in the middle of the night. It ramps up as people get up for work and school. It peaks somewhere before they go to work and school, and it goes down in the middle of the day, and then it bumps up again in the evening, come home from work and school, eat dinner, and go to bed. Weekends are somewhat different. People tend to wake up later, at least that's the theory. Well, this is all well and good. By the way, cold water and hot water tend to follow along the same basic patterns. They have to do with when we're home. Whether we're home in a house or home in an apartment doesn't matter. But it's when we're home, that's the only time we can use water when we're in our buildings, is when we're home. All right, but it actually looks like this. It's a series of very small spikes. And yes, it follows a general pattern, but it is not sine wave-ish. It is discrete. And one of the important questions for hot water systems are, what are the times between the showers? Imagine this shower and this shower are on the same shower head, but they're spread apart by how many hours? You know, more than 30 minutes, 40 minutes, the water in the pipe's going to be cold again anyway. So you're starting over again for that event. And if it's in a different place, you're still starting over, mostly because it's got to go back to the water heater. These two might be close enough together. They look like they're close enough together, so that if you'd insulated the hot water pipe all the way to that shower, and this is the same shower, I don't know that for sure, but if it were, then you'd actually have the water in the pipe would be hot enough to start the shower here right away, as opposed to having to wait for it to arrive back from the water heater. These discrete events matter for system sizing. They matter for time to tap. They matter for plumbing layouts. They matter for the architecture. And we have to get all of that right, and currently we're not. So, premise plumbing models, part one. I told you this already. The hot water events are practically random within your daily schedules. There are broad patterns, but the variation is enormous, both within and among buildings of the same type, let alone different types. Hot water distribution performance depends on where, the order, the time between them, and at time of construction, we can't predict who's going to be there or what their schedules will be. We're building a 50 to 100 year building. from the point of view of the plumbing, and we have no way of predicting the future. And the systems must provide the desired service for an extremely wide range of patterns that'll change. Hard to do. Models need to be revised. There are very few steady state uses of water in premise plumbing systems, either hot or cold, right? We have to better account for transients. They're not doing that yet. Pressure drop calculations need to be based on modern pipe and fittings and current and expected future flow rates. We need to account for the waste of water waiting for hot water to arrive. We've known this for over 20 years and we're still not accounting for it right. And we need to take advantage of pressure independent faucets and shower heads. It's time to provide water to the people. Yay, team. Right, okay, and the buckets, the machines will fill in their own time, and we don't have to worry as much about peak flow conditions if we put pressure independent faucets and shower heads in. Energy models. The energy models assume that all hot water that leaves the source of hot water, AKA the water heater, arrives hot at the fixtures and appliances. It's not true. The fact is, transient's not addressed. A significant number of draws are too short to actually reach the fixture before the event is over. So we pull water out of the water heater, move it along the pipe so many feet, and stop. We just stranded the asset of hot water in the plumbing. But the models assume it all reached the fixture as useful hot water. Okay, and they don't waste water, but they represent, in our recent analysis of a bunch of buildings in California, somewhere between 15 and 25% of the daily hot water energy use. So the water got used at some temperature and the energy got stranded in the pipes. Not smart. And for California, the best way to comply with the hot water budget is not deliver hot water. I'm sorry, that doesn't make any sense. The point was to deliver it, right? The energy models need to be revised. We should establish an equal level of hot water service so you can compare energy performance of alternatives. For hot water distribution, service means time to tap or volume to hot. They're related. A minimum percentage of daily events that must arrive as hot water needs to be established. And we need to predict the system performance with transient events and for any pattern of use. An awful lot of my colleagues are trying to figure out the optimal pattern to analyze for, and the answer is, so what? I don't care what the optimal one is. For what? For who? We need to make it work for anybody's pattern. And we need to account for the waste for those that need it. All right, we're done. I need a break to take a sip, but go ahead and do questions, Lance. We're good.
Thank you, Gary. I've got a few of my own questions related to this, but for those who have been waiting patiently on the webinar, I would open it up to anybody else first that wants to jump in. And if not, then I will start. I think a very timely question, and I think I know the answer, but since a lot of this water usage studies have been done over the last few years, many of us have become stuck at home due to coronavirus. So is there anything, Gary, that relates to our current stay-at-home situation that would change these results about water usage throughout buildings in terms of peak flows and things like this?
Excuse me. We've been measuring that in upstate New York. As I said earlier, Pete has a magic box with 4 flow meters and, I don't know, 10 or 12 temperature sensors. So we can measure a lot of things all at the same time in and around multifamily mechanical rooms. That's what we're focused on. And so far, what we have found is that the peaks don't seem to get much bigger. Total gallons per day has gone up a little bit because people they're home more. And so it's been a hot summer the last few weeks. And boy, some of the apartments he's been measuring, the use went way up. But from a point of view of pipe sizing, it didn't change much. From the point of view of water heater sizing, okay. Yes, I heard another person.
The number of events went up, but the peak flow rates did not. Is that what I understand?
That's correct. The number of events and total volume of hot water went up. I guess cold water went up a bit too because they tend to be related. But the peak flow rates didn't change substantially at all. We're still having very few numbers of simultaneous events and very small high flow rates.
Yeah, so we're used to the phrase flatten the curve. So it seems that people staying at home would probably flatten the curve with regards to water usage. Instead of everybody taking a shower at 6 o'clock in the morning, you can do
Yes.
that whenever you want through the day.
And that appears to be what's happening. We're seeing events that we suspect would normally happen between 6 and 8 in the morning being spread out at least through noon.
Okay. Now I know you invited us to ask you about the swoop, Gary. You
Yes,
said ask me later about swoop.
I did. So a swoop, by my definition, is a change of 90 degrees in direction that has no pressure drop other than that due to the length of the bend. And that's what bend supports seem to do. I trademarked the word swoop. I need to fix that on the slide here. It does have a registered trademark, and I'd be happy to discuss with any manufacturers the use of the trademark. But the idea is the right idea. Bend supports allow you to change direction 90 degrees like this by going gently around the corner. You actually have a few inches less product to make the change. So it's actually shorter pipe than if you use 2 straight pipes and a hard 90. But even if you put in them as added, you still have essentially no pressure drop other than the length of the bend itself. And so either way you look at it, a swoop is a good idea. And in logic terms, it's elbows, sweeps, and swoops. We want swoops. Where at all possible, we want swoops. And we need to teach people better how to use them. They're just, I know that several of you sell them and complain that they're not very widely used. And I agree with that. They're not. They're poorly understood.
Well, there may be an opportunity for PPI to get access to some of the data, some of the pressure loss data testing you've done on this, and somehow get that published on the PPI website. Just put some quantitative numerical information out there about the reduction
Yes.
in drop when using a sweep or swoop versus the hard 90s, which I know lots of plumbers still like to use the hard 90s because they like the appearance of the tight corners and everything else. They grew up plumbing in copper, so they keep plumbing the same way. But yeah, it's really not best for the system, slower to install and everything else. So we need to keep people in that way.
I think we also need to make sure we can figure out how to do swoops with insulation on the pipe. I didn't mention that because it didn't seem particularly relevant for this group discussions, but those buildings we've been working on in upstate New York, one of the ones we measured was built last year. I know that the energy code in New York State required insulation on the hot water pipe last year and the year before and the year before that. And I know that the building specs for that project include pipe insulation in accordance with the code on all that pipe. But we measured the temperature drop around the loop, and the flow rate around the loop indicates that none of the pipe except that in the mechanical room is actually insulated. Oops. So if you're going to put bend supports on, you want to be able to put them on so that you can actually put the insulation on and then hold the pipe in place. We have to think about that. The details have to be worked on so that we can get best practice inexpensively in the field.
Yeah, that's a good opportunity for somebody there. I've just got one more question, and then I do want to take the screen back to show the article that I just saw published by you and Pete Skinner a couple of weeks ago. But my other question, because our previous presenter that we had to share information with us all back in May 12th, Dr. William Wood, as I said at the beginning, he was talking about water quality and control of pathogens, and a lot of that has to do with the age of water and maintaining disinfectants in the water. So a lot of what you've been promoting has to do with, obviously, energy conservation and water conservation. How does that tie into the whole concept of water quality and maintaining disinfection? It seems like it's two parallel goals that you can achieve at the same time. Is that accurate?
Well, that's what I think, yes. And I think your next speaker, if I remember right, is going to be Tim Keene. He's coming up on the list. Tim and I share that view. You should ask him the same question too. And that's what struck us when we had our chats some years ago, is that we're on the same path. To improve water age, to reduce it, you need to reduce the volume of the pipe in the building. Why? Because that's the only way to reduce water age, unless you increase the flow rates. So we're given a fixed set of flow rates. That's what the law says we're allowed to install. And the only way those appear to be going is down, not up. And so if you take a given flow rate and a given volume in the pipe, there's a certain water age. If you cut the flow rate in half, you double the water age. But if you cut the volume in the pipe in half, you have the water age for the same flow rate. And so what we want to be doing is to lower the water age, which improves water quality fundamentally in the building. And if we do it on the hot side, I make my time to tap less. I lose less heat in the building by reducing the size of the plumbing, the hot water pipe. And ultimately, that goes all the way back to the architect. How many of us have looked at buildings where the water heater is over here and the furthest fixture is over there, and then they have another one up and over there and another one back that way and a third one out in the east 40? That's an architectural decision. But as an industry, our job is to make it so. We're given that set of circumstances, now put it all together so it doesn't leak. And we do our best to overcome bad architecture design. And the plumber can only make lemonade out of whatever lemons they were given. Well, let's give them better lemons, maybe a different fruit. So yes, I think they are absolutely parallel, Lance. Absolutely.
And if I may jump in, and that's partly what we're trying to prove out with the projects that we're working on. BC 2018-17 ties directly into the performance of the system. All of what Gary is talking about here is what we want to actually prove through fixtures, through setting up parallel systems of code size plumbing versus the right size plumbing, to prove that the performance of the systems don't change without, not looking at hot water delivery. That's a easy thing to calculate and to prove, but that the performance of the fixtures, that we haven't altered those by right sizing the plumbing system. So that's what, for those of you, I'm sure, picked up on that. But what Gary's talking about directly relates to Project BC 2018-17.
Lance, I had one question as well.
Sure, Gary, go ahead.
Yeah, hey, Gary, I know we've talked in the past about, the pressure compensating aerators. You had a couple graphs up on the screen. My own personal view on pressure compensating aerators is that they play a critical role going forward, such that the pressure needed at the end of the line, so to speak, is enough to deliver the water. In your opinion, what is the chances in the code world of mandating pressure compensating aerators to a performance curve and effectively eliminating those that have fixed orifices that can, grossly underperform at lower pressures and overperform at higher pressures? What I know at one time the feeling when the code was that it'd be too restrictive, but at the same time, the difference in performance is enormous between pressure compensated and not, when you're talking about, residual pressure 25 or 30 psi at the end of the line to utilize.
Great question, Gary. So the question really is, which code or standard needs to be affected? In my opinion, we could address it in a plumbing code by saying that at 20 psi you have to have no less than 80% or 70% of the rated flow, and the same at 40 psi there'd be another percentage, say 90. And I don't care what the rated flow is, but you want to follow a PCA curve. So I'm going to go back to one of them and show it here. So this is the rated flow at 2 gallons per minute. And this is what I know manufacturers can make, okay, and are being sold every day. And I know they could do these too. So what if we were to pick a standard that was sort of here as a point? At 15 PSI, I'd be 0.7 of 2. And here I'd be 0.85 of 2, just to pick two numbers off the top of my head. And if we establish that and that, then they make, oh, and it can't be more than 1.28, any, you know, whatever the rated flow is for at 60 PSI or 80. And so you could make it generic and say, this is what we want. Well, I know that the industry will come and fight it because it feels like it should be done in their standard, which is the ASME standard for the performance of faucets and showers. And I think that's the place to change it. We should just establish it there, and then everybody in the industry will be able, will look at it and say that's what we have to comply to, and we'll comply to it. It turns out that an awful lot of product is following California now, so that nationally it's easier to get 1.75, 1.8 GPM showers coming out of the box from in new, and 1.2 GPM private lavy air faucets, because that's what's going to California, which represents sort of 15% of all sales or so. The biggest dilemma we face right now in that part of the industry is certifications of the product. Whenever they change the aerator, they have to fully recertify the product line. Reasons for that I don't fully understand, but anyway, they have to do it. And so if we actually want to make the change most cost effectively, I think everybody ought to chip in a few $100 and pay for the certifications. Be cheaper than going to court, going to code hearings for 2 to 10 years to make it happen.
Yeah, I agree with you, Gary. I think the product standard is the place where that needs to change.
One of the things I didn't really talk about much is that there's a huge number of events, I mentioned it toward the end of the discussion, that don't actually arrive as hot water. Those turn out to be faucets. We do an awful lot of rinsing in our homes. We rinse a dish, our fingers, a piece of fruit, vegetables, whatever it is, and the water is flowing for a few seconds. Some of it's hot, some of it's cold. And a huge percent of those mini events never actually get to the fixture in question. We seem to use hot water, meaning 105 or hotter, to take showers and to wash dishes after meals. And we want hot water in our dishwashers, and we don't use anywhere near as much as we used to in our washing machines. Excuse me. But if you actually want hot water, you want it close so you don't wait too long. Well, all of those tiny events that don't arrive as hot water are hard to fix with better plumbing. Even if you get the plumbing really close, like, you know, within 10 feet, half of a third or more of those tiny events will still not reach the faucet as hot water. Well, what are you going to do? So it turns out that I think that the best thing there is to actually do an energy standard, not necessarily a product standard, although I think they need to be one there too. But an energy standard that says if you supply me faucets that default to cold water, and you have to start from cold water in order to get to the hot water, and there has to be a range of the faucet operation that's only cold water, right? Then I go to hot, where the mix starts in. If we could do that in energy, we know how to make the faucets. That's not the problem. There's companies already making them. But that would get rid of about half of the waste of the energy attached to those faucet events, because it would default to cold water. It would be a great win, but it's an energy win, not a water win, not a pipe sizing win.
And Gary, I've heard you describe before that the delivery of hot water has a lot to do with the velocity inside the pipe, in that if you have high velocity water, you get more of a plug of hot water pushing through the pipe, getting rid of all the cold water as hot water comes through. But if you have low velocity water, it's more like a tapered bullet shape of hot water trying to get through the middle, but you don't really push all the cold water out of the way. So essentially, you're filling up a bunch of pipe with warm water, turning that pipe into a radiator, heating the wall cavity. But like you said, not actually getting hot water at the faucet unless you're really, really patient and determined.
Yes. It turns out that the difference in viscosity between hot and cold water is rather larger than anyone would typically estimate. The viscosity of 70-degree water and 140-degree water is 70 is half that of 140. Sorry, 70 is twice that of 140. The viscosity of 140-degree water is half the viscosity at 70, which has impact on pressure drop through the pipe, right? And so when you turn on a tap, the hot water is over here trying to get into the pipe, right? It's trying to go through the pipe. And there's cold water, 70 degrees, sitting in the pipe, which you now have to displace with hot water entering. Well, that hot water entering the cold water sludge is trying to find its way through in skinny little streams, and it's losing its heat to the water as well as to the pipe. And that's why it takes 2 to 1 before hot water gets there. And if you can make it go at a higher velocity, it tends to act more like plug flow.
Yep.
Good idea. So we have to right size the system. We're looking at the trunks, the branches, and what I call the twigs. We should be sizing twigs in accordance with the device they're attached to. That's it. That should be the minimum allowed in the code. It's designed to flow at 2 gallons a minute. That's the size it should be.
And when you say that, Gary, do you design it around, so given a shower at, for round numbers, 2 gallons per minute, do you size the hot and the cold at 2 gallons per minute? Or do you use some other factor to determine the proper size?
Well, that's a funny, good question. So it turns out that those single-handed shower valves we all have now are pressure balanced in the US mostly. In Europe, they tend to be thermostatically balanced, temperature balanced, but they're there for anti-scald protection. And they are the default that most of us get these days. And so it turns out that when you go all hot, you don't get full flow. If it's 2 gallons per minute, that's the mixed flow condition, right? That's what we're rating the shower head at when it's operating. But when you go all hot, the valve is getting some cold. It has to, otherwise it can't do its pressure, its anti-scald protection function. Both sides have to provide some water to it. And so it turns out that there's no method of test for that, and there's no standard. It varies according to some insights I've been given by members of the industry from 60 to 80%. Call it 70. So if I have 2 gallons per minute, I should be designing around 1.4. You think it's 80%, multiply, design for 1.6. But it doesn't have to be 2. It is some lower number.
Great question, Rich. Does anybody else have any other questions for Gary? Great conversation here. I will let everybody know that in the project that Rich mentioned earlier, BC 2018-17, which is called Plumbing Design Testing, where we've been working on the design of experiment for a while. Gary Klein is going to be working as a consultant to help us finish up that design of experiment. Because we have to be able to specify to the laboratories that might be able to do this testing, not just how to build a plumbing system, but how to measure it with the right types of measurement devices that are showers and faucets and things like that. And Gary's been doing that kind of work in his labs for years. So he definitely has a lot of very relevant expertise there. So Gary will be acting as a consultant to help us out with that. So you'll probably hear more about that by the end of this month. This being the month of August already.
So I have one more slide, then I'll give it back to you, Lance.
Sure.
So to end, given human nature, I think it's our job to provide the infrastructure that supports efficient behaviors. We don't have control over anything in this except what we build and how we build it. We have no idea how it's going to get used, but we ought to think about things to support efficient behavior. And with that, I thank you. So I'm going to give up my screen and the show. Lance, it should be back to you.
Okay. And there's one other thing I wanted to share with the group today. Thank you, Gary. With regards to other research that you've done, you and Pete Skinner, who you mentioned in one of those pictures before, have been doing a series of articles through PHCP Pros magazine.
That's correct.
About the testing you're doing. The latest one just a few weeks ago called Insulate Dem Pipes. I found it pretty insightful. Talks about basically our hot water pipes becoming radiators, the way they transfer heat into our walls, into our spaces, unless they're insulated properly. So if anybody would like a copy of this article, I recommend you read it. There's numbers involved, so don't just skim it, really read it. But go to PHCP Pros and just search for Gary's name. Excuse me. Just search for Gary's name or search for the name of this article.
And the series started back, I think, in February or March of this year. And so we have hit 6. That's what we agreed to. It is my impression that we're going to get 1 or 2 more later this year to wrap up our current series. And then next year, we're going to ask for more articles based on the results of what we actually got built. That box you see in the picture there is what Pete calls the magic box. That's not Pete. That's our friend Hugh Henderson who put it together. We really do need more data on water flow in a variety of occupancies so that we can update the methodologies in the water demand calculator for different occupancy types. So that's another project to be thinking about, folks. We really need the data and we need to figure out how to get it for a wide variety of buildings. We don't have to do them all at once, but we better start doing them.
Yeah, you bet. Okay. Well, Gary, on behalf of everybody who joined us today, I think we had a maximum of 38 people connected at one point. I want to sincerely thank you for putting this presentation together for us today, joining us on a Monday, sharing it all with our members, all the Q&A, all the other advice you've given to us over the years, and look forward to working with you more on our research projects and a consulting basis.
Thank you all very much.
Absolutely.
I appreciate it, and I
Thanks,
really
Gary.
appreciate
Great
your industry
presentation.
support. Thank you. Thank you much.
Thank you, Gary.
Thank you for joining, everybody. Have a great week.
Thanks, Lynn.
Thank you.
Thank
You all.
you.
Thank you much.
Thank you.
Lance, stay on for a second and I'll chat with you for a bit.
You bet. Good job. That went well.
Thank you. It seemed to move along pretty well.
I'm going to stop our recording.